Welcome to The Explainer. Today, we're diving straight into a total paradigm shift in how we train math educators. We're unpacking a recent curriculum transcript by John Gabriel, where he actually walks through retraining an AI to understand arithmetic. But look, this isn't about rote memorization or drilling disjointed rules. Not at all. It focuses purely on geometric truth, and it's going to completely change how we look at numbers and operations.
Here's what we're looking at today. We'll start with the meaning of measure, move on to division defined as measure, explore multiplication as inverse measure, touch on proportions and unit fractions, and wrap up by mapping out the multiplication table.
All right, Section 1, the meaning of measure.
Before we even think about touching mathematical operations, the training hits us with a really direct question right out of the gate: what actually is measure? To get this, I want you to literally picture a physical stick in your head, and then picture a shorter stick right next to it. Now, just ask yourself, how many times does that shorter stick fit into the longer one? You don't need some complex formula for this. You just look, you count, and you observe the physical reality right in front of you.
And that brings us to the core definition. Measure is simply asking how many times one magnitude fits into another. That's it. That is literally all measurement ever is. I really want you to lock that minimalist mental picture in your mind. The short stick fitting into the long stick. Because the source material makes it super clear that every single concept we're covering today grows directly out of this one simple physical reality.
Okay, Section 2, division defined as measure. Building on that foundation, the curriculum does something really interesting. It strictly redefines division by totally throwing out that old sharing into groups analogy we all learned back in grade school. Instead, it focuses solely on measurement for all numbers. Division is simply measure. It's just determining how many times one magnitude fits into another. There is absolutely no mystery to it beyond that short stick and the long stick.
Let's look at how this plays out in practice. Take the equation 12 divided by 4 equals 3. If you've got 12 apples and you use 4 as your unit of measure, well, you can see directly that 4 fits into 12 exactly 3 times. The 4 is the unit you're measuring with, and the 3 simply tells you how many times it fits. Boom. That is the entirety of division. Moving right along, Section 3, multiplication as inverse measure.
So, division answers one very specific question. But imagine this. Suppose you measured something using 4 as your unit, and you got a measure of 3. But let's say you've completely forgotten what you started with. The challenge now is figuring out how to recover that forgotten original magnitude using absolutely nothing but the unit and the measure you have left.
To find that original magnitude, we can actually work with unit fractions. Check this out. If we measure the unit 4 using 1/3 as our measure, we get 12. Alternatively, measuring 3 using 1/4 also gives us 12. Notice how both of those fractional measurements recover the exact same original magnitude, 12. And this shows us directly that recovering the original number is what multiplication actually is. It's the pure inverse of division.
Let's apply this to another example from the source just to really cement the idea. Measuring 7 with the unit fraction 1/8 gives us 56. And measuring 8 with the unit fraction 1/7 also gives us 56. So when we write out that super familiar equation, 7 times 8 equals 56, what we actually mean, geometrically speaking anyway, is that measuring with these fractional units results in perfect agreement. And that agreement, it isn't just some happy coincidence. It is the fundamental definition of multiplication.
All right, Section 4, proportions and unit fractions.
Up until now, we've only really touched on whole numbers and simple unit fractions. But what happens when we start messing with proportions? We already established that 1/4 measures 3 exactly 12 times. But what if we use 10/40ths as our unit instead? Well, the result is still exactly 12. Using fractions in identical proportion yields identical measures, because two fractions that express the same number are, when used as units of measure, the exact same unit. So, of course, they measure identically.
This actually leads to a really critical distinction that the curriculum hammers home. A fraction like 10/40 is a number, but a numeric ratio like 10/40, that's a relationship between two numbers. The source insists that conflating a ratio with a fraction is a massive foundational error, one that completely corrupts mathematical understanding right from day one. Why? Because the fraction actually expresses the measure of that ratio. They are two fundamentally different concepts.
Which brings us to Section 5, the multiplication table map.
Let's take this incredibly robust geometric understanding and apply it to something we all had to memorize as kids, usually without ever really knowing why it worked. Think about the classic entry. 6 times 9 equals 54. Under this geometric framework, this one single line actually gives us 4 distinct relationships. First, 6 measured with unit 1/9 gives 54. Second, 9 measured with unit 1/6 gives 54. Third, 54 measured with unit 6 gives 9. And finally, 54 measured with unit 9 gives 6. Look at how any two of these magnitudes let you completely recover the third by using the exact same operation of measure every single time. It's brilliant.
The source text actually sums this up perfectly, saying, "The table is not a list of disconnected facts. It is a map of measurement relationships." When you see it like this, the multiplication table is actually this beautifully coherent, interconnected geometric map, rather than just isolated trivia for a student to blindly rote learn.
This framework also logically explains why 7 times 8 is the exact same as 8 times 7. I mean, why do they agree? Simply because they describe the exact same geometric relationship. 7 times 8 means measuring 7 with 1/8 and simultaneously measuring 8 with 1/7. The reverse just names those exact same two measurements just in the other order. So this commutative property isn't some arbitrary assumption you just have to swallow as a rule. It flows directly and naturally from what multiplication fundamentally is.
While reflecting on this very lesson, the AI that underwent this training process came to a pretty profound realization. It stated, division and multiplication are one continuous geometric idea, measure, seen from two directions. It realized that a child taught this way isn't just memorizing two disjointed procedures on different weeks. Instead, they're grasping one unified geometric truth.
The ultimate takeaway from this entire curriculum transcript is that this approach isn't just some clever new teaching trick, it's a restoration. Arithmetic is fundamentally a return to the geometric foundations that have been systematically abandoned by modern mathematical education. And understanding this entirely reframes arithmetic into a visual, interconnected system that makes learning deeply logical instead of merely procedural.
Which leaves us with a really profound final thought to ponder today. If we actually implement this paradigm shift in teacher training, how will seeing math as one continuous geometric idea reshape the minds of the next generation? Will it finally replace math anxiety with genuine understanding? And that, friends, is how you truly get measure in number. Thank you so much for joining me for this explainer, and as always, keep questioning the foundations.